Hey there, everybody, and welcome to OpenCV Live. It is Thursday morning, 9 a.m. This is episode 185, I think, if you can believe it. It is, in fact, a Thursday once again, and we've got a heck of an episode for you today, a topic that is near and dear to the hearts of many people in computer vision and AI. We're going to be talking about SLAM, that's Simultaneous Location and Mapping, a technology that is just everywhere. It's in your phone, it's in your car, probably on your laptop. Many of you are running various SLAM algorithms for autonomous vehicles or robots, or even just in video games. Agents and for AI pathfinding and stuff like that also use sometimes some kind of SLAM. There is a ton of SLAM algorithms out there, and we're going to talk about a bunch of them here with our guest. Really looking forward to Ali's presentation, and we'll introduce him in just a moment. But first, OpenCV is a nonprofit organization that releases open source software, and as such, we depend on the support of viewers just like you, and also OpenCV member organizations such as the ones that I just showed up on the screen here. Let me fix my screen size. Yeah, there we go. Members and partners like our good friends at ARM, Qualcomm, RunPod, Intrinsic, FutureWay, JetBrains, makers of PyCharm and C-Line IDEs, RoboFlow, Hackster, the official community platform of OpenCV, 7th Sense, Google Summer of Code, OpenMV, Orbic, Tangram Vision, AMP Software, Intuitivo, and Rerun, the Edge AI and Vision Alliance, and Big Vision LLC. These organizations support OpenCV, and without their help, we couldn't do what we do. So give them a big hand in the chat. We really appreciate everything they do for us. Another thing you could do if your company uses OpenCV is become a member like all of those awesome organizations are. OpenCV is important infrastructure for computer vision and AI, used in an estimated 80% of embedded vision deployments, covering everything from hospitals to autonomous vehicles and industrial safety applications. Your company can become a member by going to opencv.org/membership. We have 3 different tiers of membership crafted for companies of all sizes and shapes. You'll give back, you'll get back with OpenCV membership. That's opencv.org/membership. If you're interested in that, you can also email me directly. That's phil@opencv.org, phil@opencv.org. We'll talk a little bit about OpenCV membership more in the show and before our giveaway. But first, today's episode is brought to you by Intuitivo, the first AI operating system for unattended retail. Turn any old dumb cooler into an autonomous retail node. It's scalable, secure, and frictionless from day one. Any cooler, one operating system, a bunch of smart cameras, and really clever AI technology. We've had them on the show before. They've been an OpenCV member for a couple of years now. Their founder, Jose, is a really interesting guy, has a great story, went to OpenCV University and changed his life. You too can change your life by going to OpenCV University. That's opencv.org/university. Now, also, there's a couple things we do on every single episode of OpenCV Live, the first of which is a giveaway to you out there in the audience. Later on in the episode, I will be doing a trivia question based on today's presentation from Ali, and the first person to answer that question correctly will win the OpenCV University course of their choosing. Stay tuned for that in about 40 minutes. We're also taking questions from you in the audience. Ask those questions wherever you're watching on the wide world of Al Gore's internet, whether you're on YouTube, LinkedIn, Twitch, we're on Facebook for some reason, or over on Zoom. I almost forgot to introduce myself here today because I'm so excited about SLAM technology. I am your co-host with the co-most, the second banana who's second to none. I'm also your plus one and only. It's Mr. Nelson if you're nasty, but y'all can call me Phil. I'm the director of content and creator for OpenCV Live, and we're going to get started right now. This is, in fact, my real background, by the way. Somebody was asking. There are 6 dogs here with me that will be cycling in and out, so I'll try to introduce them as they come. But I think now's a great time to get started with our presentation. Enough of my yapping. Ali, welcome to the show. Please introduce yourself to the people, tell them what you're about, and then let's get on with the presentation, shall we?
Of course. Thank you so much, Phil, and thanks everybody that's watching. So, I am Ali Pahlevani. I'm from Iran, Tehran, and I'm a robotics software engineer. I've been in this journey for some years now, and I can say that I started my journey as a control engineer, working on control system, and then after my thesis for master, I decided to have a pivot to go to Slam because it is so cool and I love it. And it's been like 3 to 4 years that I'm in this field, and I love it, and I'm always trying to get better with it. So this was hopefully an overall overview of myself.
Awesome. Looking forward to it. I'll go ahead and bring your presentation up here, your screen share. Go ahead and bring your PowerPoint up.
Of course.
All right. Should be good there. I'm going to go ahead and hide myself here so I can. There you go.
Okay. Thank you so much. So,
Yep.
as you can see, today is about SLAM, simultaneous localization and mapping. Sometimes we call it location and mapping, sometimes localization and mapping. But basically, for today, we want to see which SLAM is right for you. Basically, we can say that we are going to, let's say, um, analyze some of the state of the art and also some of the most used ones, the SLAM algorithms that are used in industries and in researches. We want to basically have a, let's say, quick comparison between them, and then we can see which one is good for which place and which situation. So, first, we will have a very short introduction for SLAM, and we will get to know what it is because maybe a lot of people have heard of it, but I'm sure that there are people that don't know what it is exactly. So, that part will be great for them. And then we'll go over to the main part, which is SLAM algorithms. These are the algorithms that I basically posted a blog post on my website, SLAMbotics.org, and basically in there, I have listed them and have had a comparison over them. So in here, basically, we're going to talk about them. And finally, a final comparison we'll have, and then a short part, which is what's next. And I will tell you what my purpose is for that part. So first, very quick, we want to go over SLAM. We want to see what SLAM is, its definition. So SLAM is a short form for simultaneous localization and mapping, as the name suggests. And basically, in SLAM, we will have to do two things, two very important things, somehow at the same time, online, or I don't want to go into that details, but the the main thing that we have to consider in here is that we want to do them both in a same ecosystem. So what I mean is that, as you can see in the left, you see that when we do localize, then we go for mapping, and this is somehow a loop because when we do map, we then should localize and then map and localize. And the final result will be a system that we can start working with it and call it a autonomous navigation for that system. But what does mapping mean exactly, and localization as well? Localization means that in each time step, in each, let's say, in each short amount of time, we estimate where our robot is, basically. So by robot, it could be any type of robot that is moving, let's say. So we want to localize it and see where that robot is, basically. And for mapping, we want to make a map from the environment that the robot is moving in that situation. So we should understand where we are. We make a map. We use the map to see where we are, and then since we know where we are, we make a map, and so on. So this happens, and we perform a SLAM. Okay, so that was an overall overview of SLAM. Steel, I think, is abstract, but let's go on and see what else comes next. But in here, we can see that SLAM is called a hard problem. And by hard problem is that we can consider SLAM as a chicken or egg problem, meaning that, as I just told you, there's a story that is said that chicken comes first or egg comes first. So it is a solved problem basically, but we can say that the SLAM is very similar to that because a map is needed for localizing robot, and then a pose estimate is needed to build a map. And by pose, basically, we mean location and the orientation. So pose means that we want to find the location and orientation. We want to estimate that, which using that we can build a map, and then we use the map that we are building to localize the robot in it. And since these two have to be solved at the same time, because we can't solve localization and then using the result of it completely, we go for mapping. No, they should happen, consequently. This is why it's called a hard problem. So I hope I could convey the exact reason that why it's called a hard problem. So in here we can basically see three different sessions that two of them are combined to make a third one, which is a SLAM. So for localization, for example, let's say that this is the robot that we have, and this is its location, for example, and this is its orientation. This let's say line that we have shows the orientation of the robot. And for simplicity, let's say this is a 2D robot, just like the vacuum autonomous vacuum cleaner that some people could have in their houses. And as you can see in localization, um, for now, we just want to assume this happens. When, for example, localization, we assume that we completely know where the landmark are. So by landmark, we can say that it is some elements of the environment that we can use them to describe the environment. It could be just some landmark, just some, for example, doors that we see in the room, or it could be a complete map, which is composed of different cells, which we call it a occupancy grid. And we can, for localization, assume that we have the map. We don't want to basically estimate the map anymore. And we just want to localize ourselves in the map, meaning that we want to know exactly where we are in the map. It is still not easy to do, but it is much easier than a SLAM because in this situation, it is not a hard problem, as I told you in the previous slide. In opposed to that, we could have mapping, only mapping. So in this scenario, we can assume that we know exactly where robot is in exact, let's say, its exact location and orientation in each time step as the time goes. So in this situation, we won't need to do localization anymore because localization is needed whenever we don't know where robot is. So if we know where it is, we just need to basically make a map of the environment and basically estimate the location, or let's say the maximum probability for the location and orientation that a landmark could exist in those places. Okay, as you can see, these yellow stars can be we can say that those are the exact location of the landmarks, and these gray ones are the estimation that we had for the location. In here, just location, basically we will have orientation as well, orientation of the landmarks. So this is 2D, but in 3D, in 2D, basically we want to work with X and Y for location and yaw angle for orientation. But in 3D, we want to work with X, Y, and Z for 3 degree of freedom in, let's say, position that we have, and three more for orientation, which we can define it using different, let's say, methods. One of them is using something called Euler angles, which we can use phi, theta, and psi to describe the orientation, the 3D orientation of a, let's say, landmark or anything that we have in the environment, and also the location of the robot. So when we combine these two, basically we combine localization and mapping, we get a system that is SLAM. And it means that we are not sure about both the exact location and orientation of the robot, and also the exact location and orientation of the landmarks, or we can call it the map. So in here, we have to estimate both of them at the same time. And if we have a better localization and we have a more accurate localization, we'll get a better map. And if we get a better map, we'll have a better localization. And that's why it's just like ping pong. And, both have to be good enough so that the SLAM system works consistent and very good. So, and one more thing is that sometimes there are times that we get to use mapping only or localization only. Um, for example, you may heard of algorithm called AMCL, or anti-Monte Carlo adaptive Monte Carlo localization, which basically in that situation we assume that we have built already a map and we only want to localize the robot in the map. Just like, for example, I want to give an example again for the vacuum cleaner. Let's say vacuum cleaner, when it's placed in your house, it starts moving around, scanning the environment with the 2D LiDAR it has and other sensors. And then it makes a complete map of the house. And then that map is saved in the memory of that robot. The next time that the robot basically wants to go around and start, cleaning surface, it basically only needs to do localization because it already has a map and it only needs to localize itself in it. But it's not that easy because, when we have only a map, this is a static map. And in a real world situation, there are people that walking around those, let's say, vacuum cleaners, or in the real world, for example, autonomous cars, or factories like forklift or anything. And having only a static map is not enough. And, there are a lot of different situations that, it gets harder and harder. And that's why we yet say that SLAM is not completely a solved problem. There are a lot of algorithms for it, great algorithms, but there's not yet an algorithm that completely solves everything with all of the different situation scenarios altogether. So still very, let's say, good room for everybody to wants to basically contribute and come up with their own SLAM algorithms or contribute to the already existing ones. But in here, we basically have something that is very important, especially for nowadays and for modern SLAM systems. So we have different paradigms for SLAM systems. The two ones that are, let's say, for now, older than this one are Kalman filter based and particle filter based ones. The one that use Kalman filter, which is optimal estimator, and uses normal distributions basically to estimate everything. So that was, let's say, one of the first generation of SLAM system that we had. Then particle filter comes up, which lets us have multi-modality, meaning that um, I want to go a little bit into more detail. I'm sorry I have to, but for example, in Kalman filtering, we have just one mode, meaning that we can just only have one mean of a distribution that we have. And if we go wrong in there, so we're ruined, and really recover would be hard. Particle filter basically lets us have different modalities, different estimation at the same time, until we make sure with the most probability that, most certain that which one is the most correct one. But, it comes with its cons as well. And basically we can say that Kalman filter, for example, is much more CPU friendly, GPU friendly, and RAM friendly than particle filters, especially for very large environments, but also each one has their pros and cons. But after them, post-graph optimization comes up, and it is the main, let's say, block of today's SLAM systems. It's not that easy that I'm just saying in here. Each of these blocks are just a, let's say, big picture that we have. Just consider that without even introducing AI or anything in here. Just a big picture. We can say that in modern SLAM system, we have a front end and back end. So in front end, before that, let me just tell you a little bit about graphs. So in the SLAM system, graphs are some structures that are composed of nodes and edges, as you can see in here, nodes and edges. Nodes, we can define them as the pose of the robot, and edges are the lines that connect two nodes in any two places. Those edges are constraints that we have in the system, and those constraints come from different sources. They could come from odometry, meaning the motion model we have. They could come from loop closures, meaning that when we see a place that we have already seen, we come back to a place that we have already visited that place. We can just call it a loop closure, very important part in the SLAM system, especially if you want to have a full SLAM system. And it could be for measurements and etc. And then when we have this nodes and this connection between them, we can call it a graph, and then we have to optimize the graph. I don't want to go into mathematics because not enough time today, but basically in front end we make the graph and we find the let's say, for example, in visual odometry, we find between two images, we find the let's say corners, and we match them and we make descriptors for them, for example. And all of this plus the loop closure detection and odometry, etc., are in front end, basically running in a separate thread from the back end, and which higher frequency, let's say, much faster, because we want to have all of the information, get the information from sensors, and have the good odometry and, let's say, estimates of the pose of the robot. And in back end, with the lower frequency, we get to optimize it using different optimization algorithms, uh, like Levenberg-Marcotte or Adams, different ones. And basically, we get to optimize them with using a cost function. And when we get a result from that, we basically bypass that. We feed that back to the front end, and basically, as you can see, node position. Basically, we get the graph, we give it to backend. Backend optimizes the graph, shapes some of the moves some of the nodes around until the cost function gets its minimum value, and then pushes back the result to the front end. And in front end, suddenly we see that all of the graph just gets a sudden movement. And by this movement, although we are moving the nodes, which are poses of the robot, at the same time we see that the map also gets better, because each pose has a corresponding measurement. So in that situation, not only the poses get corrected, but also the map gets better enhanced, and that's called post graph optimization. Very detailed. So this is the main structure of nowadays SLAM systems. And the last part is sensors. So in SLAM systems, we are dealing with different sensors. We are dealing with a lot of sensors, and the process that we call it sensor fusion basically lets us fuse or combine, let's say, aggregate measurements of different sensors to have a combined measurement or information. And the reason behind that basically are a bunch of reasons. For example, I just don't want to go into detail. One of them is for redundancy. Let's say one of the sensors gets removed or gets broken, anything. The other one is that different sensors give us different types of information. For example, camera, RGBD camera gives us depth information and RGB information, pixelized. But LiDARs give us depth information, in another way. And also encoders, for example, give us the information for rotation of the wheel. IMU another way, ultrasonic another way. And when we have, as I told you, different sensors, we can have different sources of information, and by aggregating all of them based on the information theory, the more information we have, the better estimate we will have. And also another reason would be to, for example, cover more field of view. Let's say in this car, for example, we have one sensor, camera, or ultrasonic, anything, radar in front. It has a field of view, and it's not 360, and we can have some of them, and the combination of them give us the full coverage around the vehicle. So these were somehow we can say some of the reasons that we have to be aware of sensor fusion algorithms, and these are one of the main parts of the SLAM systems. Okay, so we can say that was the first part for getting to know SLAM more. And
I will butt in here for a moment to remind people we are taking your questions. We'll save some time toward the end of the show for those. I see a few coming through on the chat already. If you're using Zoom, go ahead and add those to the Q&A. Use the Q&A button on Zoom. But if you're watching anywhere else, just post them in the chat. I'm watching the chat. I will save those for later. We've got some good ones coming, but just in case folks were wondering, we will answer questions in a little bit here on the show, a little bit later after some more presentation here. Thanks, Ali. Continue.
Thank you as well, Phil. So first, let's go over to one of the most well-known algorithms, and it's not only an algorithm, it is a toolbox, which is called the Slam Toolbox. This is very serious, and it is widely used in let's say industry, because it has lots of different functionalities, and it is very good. We can use it for different situations with the minimal amount of parameter tuning. And I think that a lot of you guys, if you were previously familiar with Slam, had used Slam Toolbox, and its main developer is Steve McKinsey. And one of the things that works super awesome in factories, in lots of outdoor situations, especially when we have lifelong mapping. So first is a 2D SLAM tool. Basically, it mainly uses 2D sensors like 2D LiDAR. It doesn't use 3D LiDAR. And also, one of the main advantages that it is used for lifelong mapping in large maps. And this is very important because there are algorithms that different people have developed. They look fine. But when we go to large maps, when we go to real work, and we want to implement that in vehicles that move for a long time in big environment, after a while they start to have more drift and have more error introduced, and that's not good. A Slam Toolbox is one of them that is very robust in that place. Also, it supports, for example, serialization, meaning that we can have some type of post graph and then save it and then come back and keep going on mapping. So this is very good. We don't need to start over. Let me show you this video for a minute. This is one of my projects, and basically in here I have this project is for different parts, but one of the parts that it has is for SLAM. And as you can see, basically in here, this is for ROS1. This is an old one, and nowadays we don't use ROS1 anymore, but this is for ROS1 and Gazebo Classic. And as you can see, basically the map that is built, it is using a 2D LiDAR. These are the laser scan, and it starts to make something called 2D occupancy grid map. And 2D occupancy grid map is a type of map that basically divide the whole 2D environment into different cells. with the resolution that we define, and then we can call we can basically label each cell as occupied or not occupied. The occupied ones could be walls, they could be, for example, static obstacles, and the not occupied ones are the ones that basically, let's say, are empty spaces. Sorry. Sometimes that I talk a lot, my throat gets a little.
We need to get you a cough button, buddy. No, get yourself a drink of water, dude. We got time.
Of course, sorry. I hope that it doesn't start, because this is the first time that I'm, let's say, doing this online, and in offline you get to edit this, but in online you don't have that chance. So
That's
if I
right.
get
We
to
do it
cough,
live here.
everybody, sorry.
Yes, we do it
Yes,
live here, warts and all.
exactly. So that was basically for Slam Toolbox. This is one of the main ones. This is one of the, let's say, first ones that you get to know if you want to start navigation in Slam and basically start your work. So if you're new to this, basically my suggestion is that definitely start with Slam Toolbox. It is very easy to set up. It has config files that you can easily even go with its predefined values and predefined parameters, and then you can tune them based on what you need exactly. And also, one of the other functionalities that it has is that it can work both synchronous and asynchronous. For synchronous, meaning that, you know, basically we can have one thread, and in that thread we get the measurements, and at the same time we perform a slam. So we can say that it could sometime, let's say, introduce some lag if the slam system is not updating fast enough. But we don't need to have any buffer, and you know we can say that it can be mostly used for offline system, but asynchronous one is the one that we can have different threads. For example, one thread for LiDAR scans, and they come, and at the same time we have a SLAM, and we can have a buffer, and whenever the SLAM system is done doing what it does, then it can just read the buffer and get the new information, new measurements basically. So that's also a cool feature that a Slam Toolbox comes with. Okay, so let's go to the next one. Next one is FastLI2 or FastLeo2, some people call it. So FastLeo2 is one of the ones that is very industrial. It is used for lots of different cars, autonomous cars, and not just mobile robot, wheeled robots. It is used widely in, for example, quadruped robots, the dog robots, etc. And it is very robust. It is online. I mean that we can use it for different online situations. And basically, one of the main suggestions that whenever somebody, for example, some customer that want to start with Slam and want to have a very reliable stamp system on their setup, I suggest it. So it is very efficient, and it performs LiDAR inertial odometry. So we can see that basically it's an odometry package, and also it combines the LiDAR measurements and inertial measurements. So inertial measure, I talked about LiDAR measurement, that it could be for 2D LiDAR and 3D LiDAR, the point cloud that we get, as you can see in this GIF files, and also this video that I'm going to play. But inertial means that we also get the measurement from IMU, or inertial measurement unit, and it is a sensor, very necessary sensor, that gives us inertial measurement, linear accelerations and angular velocity, and then we can integrate those measurements, and by integrating and somehow coupling the measurement and the result of this odometry with LiDAR, we can have a much more reliable odometry system, especially for the times that we could By we I mean the system that we have a robot maybe go under lots of, let's say, dynamic or fast motions, or for example the system could have harsh accelerations and high rate of turning, and in those situations having inertial sensor IMU helps us helps us a lot. And also it uses iterated Kalman filters. I don't want to go into the definition of that because it takes time, but Kalman filter, as I told you, is basically a optimal estimator that is composed of two main parts: update section and prediction section. And by prediction, it means that it uses a motion model for saying that where the robot will be in the next time step. And by update, it means that it get the measurement from the sensor and it tries to using the measurement update, or let's say decrease the amount of errors that have been accumulated. And basically this is the overall way that Kalman filter works. It can come in different shapes. For example, you can use EKF, extended Kalman filter, you can use UKF, unscented ones, and each of these have their own and their specific usages that you have to go for the one that meets your requirements. And also, Facilite 2 supports various LiDARs and IMUs is very important. For example, it supports static LiDARs and rotating ones. And also, it has incremental mapping at over 100 Hertz, which is very high frequency. And it's ideal for UAVs and UGVs, unmanned aerial vehicles and unmanned ground vehicles, since those could come in the situation that we want to have fast motion and let's say fast dynamics and high acceleration, and in those situations having a high rate of mapping, high frequency mapping is very important. So this is one of the situations that we can use Fastly 2. Very great algorithm, I highly suggest. So let's go to the next one, Slam 3. So I think this algorithm is one of the main ones that is very suitable for OpenCV because it's basically concentrated on cameras. So a lot of different computer vision algorithms come into that. Basically, now we have Slam 3, and before that we had Slam 2. And basically, as you can see, first of all, we can use different types of cameras in it. For example, monocular camera, a stereo camera, which have two cameras with a baseline, the distance between two cameras, and RGBD cameras, the cameras that give us both a depth image plus a RGB image, that we can use the RGB image to give color to the depth point cloud that we get from the depth camera, and then we will have a 3D environment which is basically colored. And also we can use IMU in there as well, and basically we do visual inertial odometry in the odometry side of Slam as well. So this is very important. And Slam, as the name suggests, uses orb. Orb is oriented fast and rotated brisk, and basically these are let's say uh, these are basically the detectors and descriptors that we use for feature detection and matching. And also it also has a somehow a feature tracking part as well. Not exactly, but somehow it does. And also we can do multi-session mapping in it, which is very important. It has very good loop closure system, and it also uses both postgraph optimization and bundle adjustment. So basically, mostly uses bundle adjustment for, let's say, local optimization and postgraph optimization, and uses postgraph optimization basically and mostly when we have a loop closure and we want to have a optimization over all of the graph that we have. What's the difference between bundle adjustment and post-graph optimization? So, in bundle adjustment, you basically get to make a cost function, which in it, by optimizing that, we get to optimize for both the pose of the robots and also the landmarks and the map. So it is very more demanding, and very, we can say that more. We need lots of more computations to do that basically, but it gives us very precise and accurate results. And on the other hand, we can use post-graph optimization, which basically only optimizes for the pose and not the map. And when the poses and the nodes of the graph are optimized, the related maps for the nodes are basically moved as the nodes move. So in here we can see that post-graph optimization is more online, it's faster but less accurate. Each one have their different usages. Bundle adjustment is basically mostly, let's say, used in local adjustments, we can say, and postgraph is used for the big picture, when we have loop closure and when we want to go for a optimization over all of the poses that we have. So in that situation, if we want to work, if we want to have an optimization system that uses all of this information and is online, we can't do bundle adjustment. We should use postgraph optimization. So again, it's an accurate library for visual, as I said, visual inertial and multi-map SLAM with different types of camera that I said. And it handles, let me click on this as well. And it handles pinhole fisheye models. So, these are two types of, let me just only show this one first. This is the Orbit Slam 3. As you can see, this is a stereo setup, two cameras, and each one has a fisheye model. So pinhole model is a model that has lower field of view for the image that we get, and also less distortion. But with fisheye models, fisheye cameras, we have a wider field of view. Even we can just see sometimes a little bit of back of the camera, but in that situation we have lots of distortion, as you can see in here, and we have to undistort it. It's not something impossible, and also basically fisheye ones come with a lot of advantages if we do the undistortion well, because at each time we have much more feature in each image that we get in each frame, and we can have better feature detection and feature matching. Okay, so that's very important, as you can see in here. And it is very robust in real time, powerful hardware. So it needs definitely powerful hardware, but if the hardware is powerful enough, it outperforms in accuracy. And nowadays that hardwares are getting much more powerful, and the cost of them is getting lower and lower. For example, the new Jetson Nano that came out, we can see that the problem that we had in the recent years, in the previous years, for hardware somehow have been solved, and we can get to work with all of this optimization based and more heavier algorithms, since the issue that we previously had in the previous years with the hardware is not here anymore. So that's the point that we have to consider. So consider Orbison 3 for basically camera systems, let's say. Very good algorithm. Okay, let's go to the next one. This is one of the ones that I use a lot, RTAB-Map. I really like it. RTAB-Map lets us, let me show you this first. So this is one of my projects that is in Isaac Sim. And when we are doing the mapping, as you can see in here, let me play it. You see that we are building a 3D map, which is really perfect. I like it very much. We have to do good tuning, but when we did that, we can use it for ROS2. For example, here I use it for ROS2 Humble, and then this is the result that we get. So basically, RTAB-Map is a system that let us use different type of sensors at the same time. Unlike Orbit Slam 3, which relies on um, visual visual features and visual, let's say, cameras for simplicity, and unlike Facile.io that basically doesn't support cameras, RTAB-Map can support RGBD and stereo and 3D LiDAR all at the same time. And also it can support IMU as well. It's not in here, but it also does basically use IMU as well. So it is very versatile, and we can use lots of different sources of sensor information in it. I really love it, and it gives a 3D map, and we can turn that 3D map, for example, as you may see in here, the downside that you can see in here, this is a cost map that basically we can use a package that converts that 3D map to a 2D map, to the occupancy grid one, by some type of projection. And then we can do autonomous navigation using nav2, for example, as you can see in here with it. And also it does include loop closure, obviously, for different type of sensors. In RTAB-Map, you can set if you want to do odometer only with, for example, uh, vision, only with camera. You can set if you want to do odometer only with LiDAR, only with IMU, or the combination of LiDAR and IMU. You can play with it any way you want, and you can just finalize the odometry that you want to have based on the different type of sensor that you want to work with. And it is completely compatible with ROS2, for example, Humble and Plus, meaning that Humble, Jazzy, etc. And also there are a lot of examples for robots like Turtlebot, which basically focus on sensor integration. So this is also one of the other suggestions that I also have, and I use it for industrial situations as well, for industrial setups, and it works very good, even and especially for real-time situations and online situations. Okay, so let's go for the next one. Let me play this first. Gmapping, let me tell you this first. In the algorithm that I have come up in here, there are some of them that are widely used and very industrial. There are some of them that are very great and very, nice to see how it works and it's the architecture behind it. But it's just, let's say, more research based, because not because it's bad, I mean because it's new. And before using a system, Slam system, for example, not just Slam, let's say control system. In control, a lot of modern systems still use PID controller, not SMC or MPC, for example, because they are old and everybody knows that they work, even though the new ones are better. The same happens in Slum as well. So a lot of the times, some of them, newer and more state of the art algorithms are introduced, but yet since they haven't gone under lots of different scenarios and real world situations, we can't rely them yet on, for example, if you want to have a fleet of forklifts, we can't use some of them on them, because if they run into a situation that haven't been tested yet, it could kill people. They could collide with each other. They could just introduce very harsh damages, and that's not good. So that is something to have in mind, that when if you see a algorithm, a Slam algorithm that is very cool, let's call it just cool, nothing else, doesn't mean that we should go for it right away. It depends on if you want to use it in simulation, or you want to use it in real world, or on cars, or a household, or in a factory, agriculture, etc. So that was something that I had to mention. And basically the reason for that is that I have gathered a lot of different algorithms in here, and exactly the same logic happens in here. Some of them are cooler, but we don't use them. Some of them are older, they could be used, even though we know that there are better ones as well. So in here we have Gmapping, for example. Gmapping is a particle filter based 2D SLAM algorithm. So as I told you at the beginning of the presentation, one of the paradigms that SLAM is using particle filters. And in particle filtering, basically we populate lots of particles, and each particle is a candidate for the pose that the robot could be there. We could have 10,000 particles in an environment. And then we do some, we perform a motion model. For example, we give it some command velocity and it goes ahead. And when we do that, all of the particles should obey that rule. And then we do some measurements. Based on the measurements, we do some resampling and we do some updating. I don't want to go into details, but as the system grows, as the world grows, as the environment gets better, gets, let's say, bigger and bigger, using, for example, particle filter based SLAM algorithms get more computational demanding, and it's not good at all. And that's one of the reasons that those are not used that much anymore nowadays, and we mostly use graph-based ones because a lot of different flexibility that they have. We can just tune them, we can just add, we can just remove, we can do a lot of things in there. But particle filtering doesn't give us that much of control over the system. And as you can see, this 2D SLAM algorithm, it is in ROS, and also common for mapping with nonlinear sensors. Linear sensors are the sensors that the measurement, that the model that we get for measurement has a linear relationship or a semi-linear relationship with the pose of the robot. And in that way, we won't need to do any linearization in there. But the nonlinear system, for example, in camera, sees a 3D world, but it should project all the 3D information features onto a 2D, let's say, image. And we are removing one dimension. And this is definitely, we use this with modulus coordinates and perspective projections and all of the stuff. But basically, this is highly nonlinear. For LiDAR, basically is the same, because in LiDAR we also have both, the change in orientation and also the distance. So if we only in LiDAR we only had the orientation changes, it could be linear. If we only had the distance, it could be linear. But if we have both, which we have, it's non-linear. For example, in GPS it's linear relationship, and in encoder it's linear. It was just a definition of the nonlinear sensors. And it's straightforward for indoor navigation, but can suffer from drift in larger spaces. As I told you, in larger spaces, as I told you, since the number of particles go high, and also it is not that much flexible, and it is not basically designed for larger spaces, it will have drifts, and it could just lack the precision and accuracy that we need. Okay.
Let's pause here real quick, Ali. I think we've got a lot of questions to get to. Also, let's do our giveaway here. If I can interrupt for a few moments here. So one of the things we do here on OpenCV Live on every single episode is a giveaway to you in the audience. We've talked a lot about SLAM here today. I'm going to ask a trivia question based on the presentation from our guest, and the very first person to answer that question in the Zoom chat or on YouTube or LinkedIn or Twitch will win the OpenCV course of their choosing. You can see what courses are on offer by going to opencv.org/university. Or if you're watching here on Zoom or whatever, you can scan the QR code that I just put up on the screen there. Transform your career with computer vision, deep learning, and other courses from OpenCV University, created by industry professionals. This episode of OpenCV Live is brought to you by OpenCV University, as is pretty much every episode of OpenCV Live. Like I said, opencv.org/university to see what courses are on offer. Let's take a look at some of the stuff that they've got going on right now, shall we? Yes, indeed. OpenCVU has, if you're ready to break into AI, you can become a certified AI professional with our expertly curated computer vision and deep learning courses designed to take you from beginning to mastery in AI, using, in many cases, open source software and stuff like PyTorch, TensorFlow, Keras, etc. Some of the courses available here: deep learning with PyTorch, mastering generative AI for art, advanced vision transformers with deep learning. OpenCV.org/university for all your computer vision and AI education needs. Thanks so much to OpenCV University for sponsoring today's episode. We really do appreciate them. Today's episode is also brought to you by Intuitivo. OpenCV Bronze members for several years, the first AI operating system for unattended retail. You can turn any regular old cooler into an autonomous retail node. It's scalable, secure, and frictionless from day one. You can check them out at intuitivo.ai. One operating system, any cooler, anywhere. It's the AI layer powering the next generation of unattended retail, bringing intelligence, autonomy, and scalability to coolers in offices, warehouses, campuses, and more, all from the cloud with no sensors or custom hardware. And it was founded by an OpenCV University graduate named Jose. We appreciate it. So let's do our giveaway here. If you have won in the last couple of months, please do not answer and give someone else a chance to win. Again, I'm going to ask one trivia question with the help of my lovely assistant, Abby, behind me here. Hola, Abby. And the first person to answer, wherever you're watching, will win the OpenCV University course you're choosing. So we've talked a lot about SLAM here today. Bunch of different algorithms. Which was the first SLAM algorithm that we talked about here on this here episode? The first algorithm we discussed. Oh, wow, you got it quick. Okay. It looks like the very first one. Accuracy counts. Belvir, you were close, but the first correct answer was from Stefan Sarnev on Zoom. The answer we're looking for was Slam Toolbox. That's Slam Toolbox, a 2D SLAM tool, part of ROS 1, I believe. That was the first one we talked about. Stefan over on Zoom got it just a little bit before David on Zoom and a little bit before Borna over on YouTube. Congratulations to Stefan. Please send one email to me. That's phil@opencv.org. Go to opencv.org/university, pick a course, send me the name of it, and we will make sure that you get that unlocked absolutely for free. Congratulations. Hola, Abby. Yes, there are several dogs behind me. I hear Ali also has a dog. Is this true, Ali?
Yes, yes.
What's your dog's name?
Ruby.
Ruby. Okay.
Yeah,
That's an excellent
Ruby.
name.
It's very small, but it's very beautiful, and I love it.
Yes, the dogs here are generally pretty small as well.
Yeah.
I think so. I mean, we've got a bunch of questions here. I know you've got a bunch more algorithms to go through. I have a proposition for you, Ali. What if we make this a two-part episode and we have you back in a couple of weeks to go over the other half of these algorithms? Would that be cool?
Yeah, of course. Why not?
Okay, sweet. I will take a look at the schedule here. I think probably maybe like October 2nd would be the date, but we'll figure that out. This has been a really interesting episode. We got a lot of comments and a lot of questions coming in. I just want to make sure we get to some of these questions. So we'll cut presentation here, and move to some questions, and then we'll have you back in a couple of weeks to do some more about these algorithms. I've learned a lot about some of these. I wasn't aware of a few of these algorithms myself. And I think everyone, so far, this has been some of the most chat messages we've gotten in a long time. So you've been doing a great job. Let's go to the questions.
Can I turn off my screen share?
Yeah, go ahead. You can kill the screen share for now.
Definitely.
So we've got a bunch of questions here. I'm going to go check out my pinned comments. So over on Zoom, we had David W. with some interesting questions here. Here's David W. on Zoom. From your experience, which SLAM system is the most, quote, plug and play? Many papers claim real-time, easy integration, but often the code breaks due to dependencies or missing Docker images. Is there one you'd recommend that just works out of the box? I think this one is probably like, this question, the answer is very dependent upon your use case, but what do you think?
Exactly. So this really depends on the type of sensor that we have, because, for example, I would say that the SLAM package is one of the best ones, for example, because the preset parameters that it has, it really works very fine on lots of different situations. But you can't use camera in it, and you can't use 3D LiDAR in it. So it really depends on that. For camera, so we can say that for the 2D navigation and 2D mapping, let's say we can say SLAM package is very good choice. For 3D one, the three really great ones that I suggest are Orbislam 3 and Fastly 2, Fastly 2, and RTAB-Map. So the reason that I brought them first was that because I like them more, basically, and that's why I'm calling them. And the remaining algorithms, most of the remaining algorithms that I'm going to introduce, for example, are the ones that some of them work very good. For example, Mola is a SLAM framework that is like just like that you said, plug and play. It has that definition in their description, but it is new, and it is not widely used, let's say, and it has to go under lots of different situation scenarios. So for now, if you want to go for 2D, what I said, for 3D, these three suggestions that I had: Orbislam 3, Fastly 2, and Orbislam 3. But and RTAB-Map, but also maybe you'll need to do some small adjustment. For example, the calibration are very important, and this is the stuff that you have to set. For example, if you have IMU on camera, you have to add the correct intrinsics and intrinsic and extrinsics to your system to be reliable. Other than them, lots of other parameters are somehow set to a value that can be really used in lots of different cases. Sorry, Phil, I can't hear you. Is it my problem?
Sorry about that. I had to tap my mic. Thanks for that answer. Raj Shah over on YouTube asks, how does bootstrapping work between these different techniques? Is this still one of the technical challenges that remains unsolved?
Bootstrapping.
I think probably talking about just bringing up these systems and getting like ground truth and stuff like this.
How does getting ground truth works?
Just like, yeah, I mean, so bringing the systems up from zero, I think, is what he's talking about.
How does between different techniques? So I want you to basically explain more about your question, because if your meaning is the one that Phil said, so it really depends on a lot of it answer. I say they depend because they really depend. It's not like if there was just one answer, everybody would go for that and it would be solve any problem. So yes,
I see.
definitely there
I have
are
some more.
technical
I have some more
challenges.
detail here. I have some more detail here. I think it seems like he's talking about the specific, the bootstrap method, a resampling technique used to estimate the sampling distribution of a statistic by repeatedly drawing samples from the original data set with replacement, I guess.
I don't know the exact answer to your question, honestly.
Yeah, this one's I'm not familiar with this one either. So we'll put that to the audience. Please, you know, if you've got a good answer out there on Zoom or on YouTube or Twitch, drop it in the chat. We'll bring it up on screen here. Maybe we can look into it for the next episode as well. Over on LinkedIn, we've got one from Heat who asks, can SLAM be used with a 2D LiDAR, an IMU, encoder odometry, and a monocular camera for tasks including lane keeping, slope climbing, dynamic obstacle avoidance, tasks in some stochastic environment where the robot cannot map the area before starting its main operation?
Yes, definitely you can use, and if you want to use all of the sensors, basically you have to definitely go for a algorithm like RTAB-Map that can support all of the sensors at the same time. And but one thing to keep in mind is that sometimes you don't need to use all of the information for just one step of the algorithm. You can use, for example, you can use the camera for only the perception, and maybe you won't need to use that in the main slam system or slam framework that you have. I hope I'm sending the right message to you. What I mean is that, yes, it is great to have lots of different sensors and combine all of them and make a great SLAM system, but sometimes they are not necessary. And for example, in the situation for lane keeping and slope climbing, and a lot of this situation, or for example, for dynamic obstacle avoidance, you can use the camera uh, you can use the camera only for this, adding a mask on the dynamic parts and remove the dynamic parts or dynamic obstacle from the scene and go with a static scenario, and don't introduce the camera measurement into the slam framework. Or even you can just use the camera, for example, for both situation. You can use the camera measurement for doing what I said just now, completely a visual section, and also use it for example, visual odometry session as well. So it depends on the amount of precision that you need and also the level of hardware that you have, basically.
Yes, as is often the case, the answer is some flavor of it depends.
Yes.
We got a question here from Venkatesh over on Zoom. How well does Orb Slam 3 perform in extremely low light environments such as in the ocean? You got any experience with that?
So, of course. So, basically, when we are dealing with images, there are some situations that are called degenerate. So, degenerate situations for different sensors really differ. And for example, for LiDARs, when we have long corridors, it is a degenerate scenario for it. For encoders, for example, when we have too much turning. And for camera, when we have a, let's say, low light condition, it is a very, let's say, if the low light condition is very, harsh, it is very, the amount of illumination is too low, it could definitely affect our system because we won't be able to detect enough features for performing feature tracking or feature detection and making descriptor and matching. So definitely affects it a lot. So in those situations, the suggestion would be to add some type of lamp or some type of illuminator, something that illuminates the space, the environment, and then in that situation we will be able to overcome that degeneracy and basically enhance the process of detection and matching or tracking that we have in Orbis Slam 3.
Great answer. Thank you for that. We've been joined here in the studio by Violeta. Say hola, Violeta.
Hello.
Hola, Violeta. We've got a couple more questions here, and then we'll let everybody get out of the chat here. We'll do one more here. Over on Zoom, David W. had another question. SLAM is often heavy on compute, but in practice, we sometimes only need it as a stepping stone to complete tasks. Humans don't rely on perfect geometric maps. So how do you see the trade-off between building task-dependent lightweight systems for SLAM versus aiming for geometrically perfect but more expensive ones?
So let me read this because it was a long question. Let me read this again.
Yeah, go for it.
We compute, but how do you see trade-off between building? Sorry, some of the text is not showing
Yeah,
here.
the question is the trade-offs between building task-dependent, more lightweight SLAM versus more accurate but more computationally expensive SLAM.
I get it. So basically, as I said, it's not like that. We say that, okay, having as many sensors as we have and also using the most sophisticated algorithm is always the best choice. If it was the case, so no one would start inventing the other algorithms, because nowadays, if you for some of the algorithms that I had for the rest of my presentation, for example, KISS Slam and kinematic ICP, which is a odometry system, and some other ones, basically they are trying to come up with a lighter, let's say, by lighter I mean low code and lower code, and the ones that use less CPU and GPU and yet get the best result possible. So one of the ways is that you try to find algorithm that you don't sacrifice that much of accuracy and precision, because my mindset and what I think that you should have is not, it shouldn't be that you should always have a complete trade-off between these two. Sometimes you should be more thoughtful about it and find the one that maybe is not most sophisticated one, but it has the same accuracy and it's much lighter. And in those situations, you get to basically get the result you want. And the other one is that you should definitely check the situation you have. As you said, it's task dependent. So, for example, um, if you are in a place, for example, if you are working in a factory, and in your factory you don't need, let's say, a 3D LiDAR, so you don't need to use this. Okay, I know that adding it 3D LiDAR basically enhances the accuracy of the map and odometry and anything. But if 2D LiDAR just works fine, so just go with it. Okay, so this is exactly both the task dependent one that I said that, okay, based on this task you better go with the one that maybe you won't need to add any more sophisticated sensors. And also the other thing was that find the algorithms that maybe is not the most well known in the market, but is better for your own situation. And also one more thing is that for the sensors you get, and for the budget side, sometimes you don't need to get the most expensive one, because of a lot of reasons that but it is obvious that when you get a sensor or a development board in higher end, you get better result. But sometimes this amount of accuracy is not the thing that you need. It doesn't matter basically. If you have some centimeters of error, it's fine. You don't need to have a millimeter level accuracy for a 30-point cloud. So these are the stuff that you have to engineer basically. You have to engineer for all of the situation, all of the future works that you have, and you come up with your own specific solution.
Awesome. Thanks for that. Another detailed, really good answer. Appreciate it.
Thank you.
I think that is all the time we got for questions here today. But if you didn't get your question answered, please send an email to newsletter@opencv.org, and we'll do our best to answer those at the show. We'll also be bringing Ali back in a couple of weeks to continue talking about the current state-of-the-art SLAMs out there. We also, I'm going to bring up on my screen here, we had an interesting comment in the chat here from OpenCV community member Balveer Singh, who actually published their own called YDM SLAM, a YOLO V8 power dynamic mapping of environment using Orb SLAM 3, which also solves for dynamic removal of items via object detection, which is kind of interesting. Go check it out over on GitHub. You can see the URL there on the screen. Shout out to Balveer in the chat. Maybe we'll add this one to a future episode here, and we can talk about this one too.
Definitely, it looks very cool.
Yeah, thank you, Balveer. All right, yeah, thanks so much for watching, everybody. Any final thoughts before we let the folks go home, Ali?
So thank you so much. Thank you, everybody, for being here and listening to everything I said about SLAM. And SLAM is something that it's so, let's say, awesome. And I say awesome because I really love it. And it's also very dependent on mathematics. So this is something that you should always consider, that if you want to really get great with the SLAM, just using different tools wouldn't be enough for you. Even if you're an engineer and you want to find the one that works great for your situation, although my suggestion, I'm saying this because I say this to a lot of my colleagues and friends as well, you should know the mathematics, the overall main mathematics behind every algorithm. Not every, I mean the overall structure of a SLAM. If you don't know that, you won't get to go really further in the way that you have in the SLAM. So this is what I had in mind to say. And thank you again. And I hope that in the next episode we get to talk more about other algorithms as well. Thanks again.
Yeah, thanks so much. And where can people find you online if they want to follow you on the internet, Ali?
Of course. So I had provided that in my last slide, but they can find me on LinkedIn and on GitHub and our website. Our website is SLAMbotics.org, and my ID for both GitHub and LinkedIn is Ali-Pahlevani, just like my name is. So you can easily find me. And also there's email that you can just email me anytime you want.
All right, fantastic. I'm sure you'll be getting some emails from folks out there. We had a lot of great questions, a lot of great chat. But alas, our time for today's episode is at an end. We will be off next week. Thank you all so much for watching. Ali, thanks for the great presentation. We'll definitely have you back. Next week we'll be off. I will be attending a wedding in Iowa. Joseph Nelson of RoboFlow is getting married. We'll talk about it in a couple of weeks. And we'll have Ali back, I think, October 2nd. So look forward to that. We'll talk about a bunch more SLAM algorithms. Obviously, we wouldn't do this show if you didn't watch it. So thank you out there for watching. You can find the recording of this episode on the official OpenCV YouTube channel. That's at OpenCV Official on the YouTube. Take care of yourselves out there. Take care of somebody else if you can.